Choose the best plastic for your application. My name is Cliff Medling. I'm going to be your host, and we're going to jump right in as we have a lot to get started in just 22 minutes. And with that, I wanted to introduce our two presenters today. First of all, Peter Rosinski. Peter has over 15 years of engineering simulation software experience with roles leading product management and marketing organizations. He holds a bachelor and a master's degree in plastics engineering from UMass Lowell and is currently the product manager for SolidWorks Plastics. Andrew Gross is a territory technical manager for SolidWorks. He has over 7 years of simulation software experience and has held roles in managing engineering simulation teams and product marketing. He has a bachelor's degree in chemistry and a master's degree in mechanical engineering from UCLA, where he specialized in solid mechanics, manufacturing, and design. And with that, Peter's going to start us off. Peter, it's all yours.
Thanks for that great intro there, Cliff. All right, everyone, so we have a lot of material to cover today. We have basically about 4 years' worth of material to cover in 22 minutes. So jumping right in here. Number one, why use plastics? We're going to, this webinar is about plastics material selection. That's what we're going to focus on here today. Why use plastics in the first place? Where they're lightweight, they have very high strength to weight ratios. They're, in some cases, have very good chemical resistance. You can get plastics with high impact strength. They're very easily customized. We're going to talk a lot about that today. They're great insulators, both for electrical, thermal, and noise. They have great optical properties if you use the right type of plastic. And overall, compared to, let's say, metals, for example, they have relatively low manufacturing costs. That's because they require lower temperatures and lower pressures to process than, for example, metals. Further to that, we're also going to focus on the specific manufacturing process of injection molding here today. So there's a lot of different types of manufacturing processes that you can use to convert plastic pellets into finished parts. But today we're going to focus on injection molding. Why injection molding? In fact, it's the process used to manufacture probably at least 80% of all the plastic parts that you come into contact with in your daily life. You can produce very complex geometry and net shape. That means when the plastic part comes out of the mold, you don't have to do anything to it. You don't have to machine it. You don't have to paint it. You don't have to trim it. It's ready to go. Injection molding is typically used for high volume applications where you want to make hundreds of thousands or a lot of times millions of parts per year. It's a relatively fast manufacturing process. Typical injection molding times are in the range of about 3 seconds on the low end to maybe 60 seconds on the high end. Of course, you can have seconds, but that's a typical range. And overall, when you finally get your molded part, the cost of that part is relatively low, typically pennies on the dollar for a molded part. So with that, I'm going to hand it back to Cliff for just a few seconds here for poll question number 1.
So great, thanks, Peter. So if you can see on the screen there, a simple yes or no question. Are you involved in the design or manufacture of injection molded plastic parts currently? It looks like half of you have already voted, so give everybody a few more seconds to vote, and then I'll close the poll and share the results. So 63% are currently yes. So let me hide that, and back to you, Peter.
Excellent. All right, so now to talk about the very basic type of plastics. There are 2 basic types of plastics. The first is called thermosets. There's no particular order here, by the way. First materials we want to talk about, they're called thermosets. They have very high strength compared to thermoplastics, which will be the second group that we'll talk about. You can use them in end-use applications which require very high temperature resistance. So one of the best applications I like to point out for thermoplastics, if you have a Weber gas grill and there's anything that's plastic on it, chances are that's a thermoset material, very high temperature resistance. Excellent dimensional stability, but one of the, it's either an advantage or a disadvantage depending on how you look at it. Thermosets cannot be reused or recycled, and that's due to the chemical cross-linking that occurs when you manufacture those materials. So when they get manufactured, there's a chemical reaction that occurs that's not reversible. So you can't reheat, remelt, or reshape thermoset materials. The next broad group that we want to talk about is thermoplastics, and those are the materials that we're primarily going to focus on here today. They are the most common and the most widely used plastic materials. Most plastic parts that you touch are made out of thermoplastics materials. They are very highly customizable to achieve specific properties. And one of the great things about thermoplastics, they can be reused, they can be recycled, so you can reheat, reform, and reuse thermoplastic materials. Now, even among thermoplastic materials, we have a couple of different broad groups. One is amorphous, one is crystalline. We won't go into the technical details of what that means, but it's just enough to know that amorphous materials are plastics like polycarbonates, acrylics, polystyrenes, PVC, ABS, for example. Crystalline materials, those are materials like high-density polyethylene. I call that milk bottle material. So if you have a plastic milk bottle, chances are that's made out of high-density polyethylene. There's low-density polyethylene, your polypropylenes, nylons, and so on. So two broad groups there. What's the difference between those materials? If we take a look at some various properties of plastic materials down the left side column of this table, and then we compare amorphous to crystalline. So for example, if we talk about optical properties, if you were ever going to use a plastic material in a lens application, so say like an eyeglass lens or a magnifying lens, guaranteed it will be an amorphous plastic because only amorphous plastics are completely transparent. And depending on the amorphous material that we're talking about, you can get optical properties which approach that of glass, for example. Whereas crystalline materials, usually the best optical properties they will ever achieve is opaque or translucent, again at best. Chemical resistance, another property we might look at. Amorphous materials, some of them do have good chemical resistance, but in general, amorphous materials are susceptible to attack by lots of different chemicals, whereas crystalline materials, because of the structures that set up inside of the material due to the crystalline nature, they typically have very good to excellent chemical resistance. So for example, if you saw a plastic gas can, that's usually made out of high-density polyethylene, which is a crystalline material. And you can see some of the other properties there that you can compare. Now, in some cases, if we talk about toughness and brittleness, for example, you can certainly have both amorphous and crystalline materials which exhibit the quality of being tough. However, if we talk about brittleness, it's usually only the amorphous materials which will exhibit brittleness in certain instances. Now, on top of all of that, I mentioned that all these materials can be very easily or highly customized. That would be through the use of fillers, additives, reinforcements, polymer blends, and that list actually goes on. So in this table here, we look at things that might be added to the plastics in concentrations of parts per million, so relatively very small amounts, to sometimes up to 50% by weight or even higher than that. These include things like colorants, UV stabilizers, flame retardants, foaming agents. We talk about blends might be other plastics. You add one plastic to another plastic, fillers, reinforcements to make the material stronger, glass fibers, and so on. And this list goes on and on and on. Now, why is all of that important? We talk about different plastic materials. We talk about different things that you can add to the plastics. That's because when we talk about different plastic materials, they all have different properties and they process differently. So you would typically, a lot of times you wouldn't use two different plastics in the same application because they have different properties. Within a class of materials, the properties and the processability can vary drastically. So for example, we talk about polycarbonate. That can be used to make DVDs or bulletproof glass. I'll talk a little bit more detail about that in a few seconds. Take a material like PVC, polyvinyl chloride. That can be used to make a very flexible rain jacket to very rigid PVC pipe. Now, We add fillers, additives, reinforcements on top of all of that. They affect all of those things, even down to the point where if I take the same plastic and make it 2 different colors, I can get very different materials. So blue polyethylene, for example, may behave very differently from red polyethylene. And that's just due to the nature of the colorant that gets added to the material. With that, I'm going to hand it back to Cliff briefly for poll question number 2.
All right, this one a little bit harder, more than yes or no. So what percentage of the parts your company designs or manufactures are made from plastic materials? 25%, 50%, 75%, or all of them? It's like half of you have already voted. Thank you. Give about a few more seconds to respond. And I'll close the poll now. And 43% of the 25% range, followed by 50% is 18%. So great. That's great results.
All right, good. So you guys using a lot of plastics out there. So now, you know, again, keeping with the theme of customization, I talked about polycarbonate just briefly a couple of seconds ago. Polycarbonate, one of the ways to customize it is through polymerization, when you actually make the material. Now, that's not just specific to polycarbonate. You can do that with a lot of plastics. And what I mean by that is that during the manufacturing process, you know, when you're actually, when a material supplier is making the polycarbonate, one of the properties that they can control is the molecular weight. Now, if they achieve a very high molecular weight, you can use that polycarbonate to make bulletproof glass. And I have the glass in quotes there because bulletproof glass is typically plastic. It's actually not glass at all, and it's typically polycarbonate. Very high molecular weight polycarbonate. It's very tough and ductile, but it can be very challenging to process because of the high molecular weight. That just means you might need, you know, high temperatures and high pressures to process that material. If through polymerization I achieve a polycarbonate that has a very low molecular weight, now I've got a material that I can use in very thin-walled injection molding applications such as DVDs or CDs. Now, one of the things about that is that, you know, that material, that's going to be very brittle compared to the bulletproof glass, which is going to be very tough and ductile. So same material, I just change the molecular weight, and I have, you know, in end-use applications, I really have something quite different, you know, from one to the other. Another way to customize these plastic materials is through polymer blends. So I take plastic A, I add it to plastic B. So again, getting back to polycarbonate, very good strength properties, very high temperature, relatively high temperature resistance, again, very tough and ductile. Can be difficult to process. With plastics, usually the, you know, the better the physical properties get, the harder it is to process that material because you need higher temperatures and higher pressures. And one of the disadvantages about polycarbonate is that it has very poor UV resistance. So if you ever see, sometimes you might see polycarbonate used in headlight applications on an automobile. If you ever see an automotive headlight lens that's turned yellow, guaranteed that's polycarbonate, and it's turned yellow due to the attack from UV rays, you know, from the sun. So usually what they do with those, with polycarbonate in a headlamp application, is they coat it with a, you know, with a material that's not susceptible to UV attack. If we look at ABS, that material has very excellent impact strength and toughness. Those are two of the best things about ABS. It's lower cost versus polycarbonate. It has very good UV resistance, and it also has probably better chemical resistance than polycarbonate. Now, I might, you know, through customizing or through blending those two materials together, I can create a polycarbonate ABS blend, which basically takes the best of both worlds. So very good impact strength, strength and stiffness, which is between the polycarbonate and the ABS, better heat resistance compared just to ABS, good UV resistance, better low temperature impact strength and ductility due to the rubber present in the ABS. It's easier to process than the polycarbonate, and because ABS is a lower cost material than polycarbonate, the overall blend would be lower than polycarbonate as well. Now, I'm going to go over this very quickly, but ladies and gentlemen, when you're designing a part that's going to be made out of plastic or really any other material for that, for that matter, you should have some kind of a design requirements checklist. Now, I'm going to present this information here very quickly, but if you go down your design checklist, that's going to help you. That's probably one of the best things that will help you choose the right material or the best material for your application. The first thing you want to look at is function. What is that part going to do? What's the lifetime of the part? Is it a disposable that you only need for a couple of minutes, or is it something that you want to last for decades? Do you need agency approvals on that? For example, UL, FDA, mil-spec, and so on. Is it going to be something for a medical device that might be implanted in a human? Is it going to come into contact with humans in its end-use application? What kind of electrical characteristics? These lists go on and on here. Chemical resistance, moisture resistance. Will your part get assembled, be part of an assembly? Those considerations. This list goes on and on. Again, is it a one-time use adhesive? So if it gets assembled to something else, you have to take into account the chemical properties of the specific material. Will it be mechanically fastened, and might you have to do something like mold in threads so that you can screw something into your finished part? Will it require snap fits? When we talk about plastics, some materials are appropriate for snap fits, some materials are not, because some materials might be too stiff and brittle, so that when you try to do a snap fit, the snap fit just breaks off. And again, the list goes on and on and on. Even another, another set of the list here. What's the weight of the part? And sometimes with plastics applications, the plastic part actually winds up being too light. Meaning too light where someone picks up the part in the hand and it just doesn't feel as heavy as it should feel. So it's actually a purely aesthetic requirement here. And I've seen applications where manufacturers will actually add a metal to the plastic just to make the part heavier, so it feels better in someone's hand when they pick it up. Something to think about. Will your parts have to be sterilized? Again, in medical devices, and that's really important to consider, because some plastics can be sterilized using some techniques. Other plastics, you might have to sterilize them using other techniques. Maybe one of the final things to think about: what's the absolute worst case scenario your part could get exposed to? Sometimes we like to think that the parts that we develop or the products that we develop are going to be used under ideal circumstances, when oftentimes the consumers take our products and use them in ways which we never imagined. So it helps to try to think of what's my worst, absolute worst case possible scenario. With that, I'm going to hand it back to Cliff for the final poll question related to plastics.
Excellent. So when finalizing your choice of plastic materials for a given end-use application, how often do you think your company picks the best material on the first try? Is it all the time, most of the time, some of the time? We could do better. And of course, we should stick with metals. So I'll give everybody a few more seconds here to respond. It's like 75% have responded already. All right, I'm going to close and share the results. So good results there. The top one being most of the time. So,
all right,
excellent.
Thanks for that, Cliff. Now I'd like to introduce to you one of our products. It's called SolidWorks Plastics, which helps you actually choose the right plastics material for your application, predict and avoid manufacturing defects, eliminate costly mold rework, and improve your overall molded part quality. We've got 3 packages of SolidWorks Plastics. The first one's called SolidWorks Plastics Standard. That's targeted at part designers. Helps you answer some very basic questions. What material should I use for my application? Will my part be able to fill, and where are the weld lines and air traps? Those are manufacturing defects that can occur during the injection molding process. The next package is called SolidWorks Plastics Professional. That's more targeted at mold designers and mold makers. helps you answer the question, will the mold fill? And it also helps you balance and optimize runner systems and gates. And then finally, we have SolidWorks Plastics Premium. That's for in-depth analysis. It will predict whether or not your molded part will warp, and you can use that package to optimize cooling system design and determine your overall cycle time. Now with that, I'm going to hand it over to Andrew Gross. So he'll take you through a nice little demo of SolidWorks Plastics. So with that, Andrew, you can take it away.
Hey, thanks, Peter. My name is Andrew Gross. I'm a Territory Technical Manager at SolidWorks, and figured it'd be a good chance to show you SolidWorks Plastics and show a short demonstration of how we can use SolidWorks Plastics to answer some of those tough questions that Peter brought up in the earlier part of the webinar, you know, when you're choosing which type of materials based on mechanical properties and manufacturability. So this is a simple part. It's a door bezel that you would find on the inner door panel of a car, and we're going to look at a couple materials and see how it's manufacturable based on the different materials we choose. So the first analysis we're going to look at here is using ABS, and we chose ABS first because it's good price point. It's tough, and it would be a perfect material for this. So the first thing we may want to do is obviously we're going to choose a material, and next we'll choose an injection location, and we're just going to choose just over here on the side. Next we'll look at some process settings. And what we've determined here is that the injection pressure limit of 8,500 psi is appropriate. We really want to stay below 10,000 psi, so we've added a small safety factor in there just in case there's any other pressure losses further upstream in the system. We want to keep that pressure low, to reduce things like warpage and residual stress of the material after the injection mold. So when we move on to results, a great way to look at results in SolidWorks Plastics is through an animation, and we can quickly see here that this is not manufacturable based on the material, the gate location, and this geometry. This is what we call a short shot. So unfortunately, we wouldn't be able to use ABS here, but using SolidWorks Plastics, we can determine that problem really early in the design process. So now on to, say, choosing another material. It's really easy to copy an analysis and just change the material here in SolidWorks Plastics by creating a new configuration. So in this case, we're now going to look at polycarbonate. It's more expensive, but sometimes can be a little bit more manufacturable. We have the exact same injection pressure limit that we determined for our ABS analysis. Now let's go on and take a look at some of these results. Again, we use an animation to look at some of these fill results, and we can see that this fills completely, and that's great news. But we also may want to look at some of the maximum pressure that takes place through the cycle of being filled. And what we can see here is that we're nearing 7,000 psi. That's really close to our upper limit. And that may be a little bit too much pressure. You may see a little bit too much residual stress in that result. So what might be a good alternative is to go to a PC ABS blend, which is going to be possibly better price point and could be even more manufacturable. We'll go straight to look at some results here. All the process conditions are exactly the same. And when we go to animate, we can see that we get a full fill. And when we take a look at some of the pressures, we can see that we're at about 5,800 psi. So a really great result. We end up with less pressure and a more cost-effective material. So thanks a lot, guys. And I'll turn it back over to Peter now.
Thanks for that, Andrew. So with that, I'm going to summarize the presentation. In order to follow the best practices in plastics material selection, you always want to make sure that you know the advantages and disadvantages of your potential material candidates. You also want to design for the manufacturing process. So today we talked about injection molding. If you were using plastics in a thermoforming application or extrusion or blow molding or something like that, you want to make sure that you're designing your parts for the manufacturing process. You'll want to follow a comprehensive design checklist. You can almost never think of every question or every potential scenario that your parts and applications might get exposed to. And then finally, it's always a good idea to use simulation for validation whenever possible.